So imagine you are a master plumber, right? And you get called in to fix this massive catastrophic leak in a 90-story skyscraper.
Yep.
I mean, water is just pouring through the ceiling on the 40th floor.
Yeah, the symptom is incredibly obvious. You walk in and you see exactly where the damage is happening. There's water everywhere.
Exactly. But to actually fix it, the building manager hands you just a basic architectural blueprint.
Right, which isn't going to help you with the pipes.
No, not at all. It shows you the dimensions of the rooms, maybe points out where the bathrooms and the kitchens are, but it contains absolutely no information about the internal plumbing. You have, no idea how the actual pipes connect inside the walls, onto the floors, or between the different levels of this huge building.
So you are left with pretty much no choice but to start tearing down drywall at random, just trying to trace the water pressure backward to its origin source.
Yeah, it's wildly inefficient.
Oh, completely. You are almost certainly going to get lost in the walls.
And that lost plumber is exactly what an AI coding agent feels like today when you drop it into a massive, real-world GitHub repository.
It really is the perfect analogy.
Welcome to the deep dive, everyone, because today we're looking at a foundational state-of-the-art paper from researchers Shad Sedek and Fatem Effard at the University of British Columbia.
And we're going to be exploring a breakthrough solution they developed called Arise.
Right, which essentially gives these AI agents a literal interactive map of the code, so you don't get buried in information overload. We're getting right to the edge of generative AI today.
Yeah, and this addresses one of the most stubborn roadblocks in AI software engineering right now because, AI coding agents seem practically magic when you ask them to write a short, isolated snippet of code.
Oh yeah, you ask for a quick sorting algorithm or like a single function to format a date.
And it generates it flawlessly in seconds. It's amazing. But the moment you drop that exact same AI into an enterprise code base with hundreds of interconnected files, tens of thousands of lines of code,
The illusion breaks.
completely, it gets hopelessly confused.
So to really understand how Arise fixes this, we have to look at why a large code base is such a labyrinth for an AI in the first place. Because, think about it. These models are trained on billions of words. They have read the entire internet. Why can't they just read the code and fix the bug?
Well, the struggle really comes down to how they process context and specifically how they search for information.
Right.
Current AI agents typically operate on what we call flat bags of files. So when a bug report comes in, they might use a traditional algorithm, like BM25 retrieval, to figure out where to look.
And BM25 is essentially a highly tuned keyword search.
Right, exactly. It scans the entire code base looking for files that contain the specific words mentioned in the bug report. It's much like an old school library catalog.
Which, sounds logical, until you realize that in a massive software system, variables and functions are often named with really generic terms. Or the bug report describes a symptom rather than the underlying cause.
Right, a user might just say the screen froze. So the search might return 50 different files that mention the word timeout or connection.
That's a lot of drywall to tear down.
Yeah, it is. Now, in slightly more advanced setups, developers will give the AI basic structural graphs. So the AI knows that, say, file A imports file B, or that class X contains function Y.
So it has the basic blueprint of the rooms in our skyscraper.
Exactly. But real-world software bugs rarely live neatly isolated in one room. They almost always involve complex cross-module dependencies.
Right, like a variable might be defined in one configuration file,
Pass through a validation function in a second file,
manipulated in a third.
and then finally cause a catastrophic crash in a completely unrelated fourth file.
It's wild. And this brings us to a really crucial concept from the research. There have been extensive empirical studies on automated program repair, or APR.
Yes, the APR studies are fascinating.
And those studies reveal that generating the actual fix, writing the new lines of code, that isn't the hard part for the AI.
Not at all.
The absolute biggest bottleneck is fault localization.
Fault localization is the binding constraint on the entire repair process, period. The data shows that if the AI cannot pinpoint the exact function and the exact line of code where the logic originally went wrong,
It physically cannot generate a valid patch.
it is flying blind. If it can't find the exact pipe that burst, it will just start guessing.
Or worse, right? It starts hallucinating fixes for code that isn't actually broken.
Oh, that happens all the time. The AI might see that the bug has something to do with the checkout cart crashing, so it just aggressively rewrites the entire checkout cart file.
Just hoping its new version miraculously bypasses the hidden error.
Yeah, and in a massive enterprise codebase, you cannot just rewrite a whole module and hope for the best. You need surgical precision.
Function level and line level localization.
Exactly. And that is exactly where the current structural graphs fall completely short. They tell the AI that function A calls function B, sure, but they offer zero visibility into how a specific variable's value mutates as it travels between them.
Okay, so enter ARISE.
Yes.
The acronym stands for Agentic Repository Level Issue Solving Engine, which is quite a mouthful. But what it fundamentally does is give the AI X-ray vision for the codebase.
X-ray vision is a great way to put it. It builds what the researchers call a multi-granularity program graph.
But the massive breakthrough here isn't just mapping out the broad structure, right?
No, the true innovation is a technique called data flow slicing.
Okay, explain that for us.
So the system uses static analysis tools to analyze the code before the AI even sees it. It mathematically tracks the definition and use of every single variable down to the exact statement level.
Wow, down to the statement level.
Yeah. The graph contains specific edges called data flow use, meaning data flow defined to use, and data flow use def.
So instead of just knowing that a variable exists somewhere in a file, the AI can query exactly where a variable was born and track every single place it goes to work afterward.
Exactly. Let's visualize how this X-ray vision operates in practice.
Okay.
Imagine a bug report says the final discount price on a customer invoice is calculating incorrectly.
A classic e-commerce bug.
Right. With ARISE, the AI agent can look at the line where the final discount is applied and say, trace this backward for me. It runs a backward slice along those data flow use def edges.
Ooh, so it just skips all the noise.
It instantly bypasses all the irrelevant code and returns the exact statement. Maybe that's 50 lines higher up or in a different function entirely, but it finds exactly where that specific discount variable was originally defined or modified.
Okay, wait. I'm skeptical here, and I know some of you listening might be too.
Sure, lay it on me.
Giving an already confused AI a complex new interface with more buttons to click, I mean, doesn't it just get more distracted? How do we know the AI isn't just getting lucky by having a new search tool to play with?
That's a very fair question.
Because sometimes if you give an LLM too many tools, it forgets what it's supposed to be doing. So is it the tool interface that's helping or the actual underlying data?
Well, the researchers anticipated that exact skepticism. To isolate whether the AI was just benefiting from a new interface, they ran this brilliant ablation study called ARISE course.
ARISE course.
Okay.
They effectively took the engine apart to see which specific piece was making the car go fast.
How did they set that up?
Well, in the ARISE course experiment, they gave the AI the exact same tool interface.
Okay.
The agent still had the ability to call a function asking for a data flow slice. But behind the scenes, the researchers secretly removed all the statement-level data flow nodes from the graph.
Wait, so they gave it a fake button?
Essentially, yes, a placebo button. The AI could click the button, but the tool would only return an empty result or just generic structural data. It forced the agent to fall back on basic structural exploration.
So it had the illusion of the tool, but the actual X-ray data was stripped away.
Exactly. And the results, performance completely tanked.
Really?
Yeah, dropped all the way back to the baseline. It performed no better than a basic structural graph system.
Oh, wow.
Which definitively proves that the data flow graph itself, the actual mathematical mapping of how variables are defined and used, that is the active revolutionary ingredient. It's not just a user experience trick keeping the AI focused.
No.
Yeah.
This structured statement-level data is fundamentally better evidence for the model to reason over.
But, knowing this map exists is one thing. How the AI interacts with it dynamically is a whole different challenge, right?
Oh, absolutely.
Because it can't just download a million-node graph into its brain all at once. That would instantly overload its memory constraints.
Right. Every large language model has a strict context window limit.
Yeah.
You simply cannot feed an entire enterprise code base into the prompt. It'll just crash or forget everything.
So how does ARISE handle that?
It facilitates a highly structured, interactive process divided into a visual three-phase pipeline.
Okay, let's break that down.
Phase 1 is graph construction, which we just covered. That's using static analysis to build the map before the AI even gets involved.
Got it.
Phase 2 is the toolset, which is divided into 3 distinct tiers. And Phase 3 is the agentic loop, where the LLM iteratively uses those tools to hunt down the bug?
The 3 tiers in Phase 2 are really the secret sauce of how the agent navigates without getting overwhelmed. I like to think of this tool set like a detective dropped into a giant, unfamiliar city.
I love that analogy. Let's run with it. So Tier 1 is all about structural retrieval. It includes tools like search entities and traverse relations.
Right, so this is our detective trying to find the right neighborhood.
Exactly.
The bug report mentions, say, a database connection timeout. The detective uses Tier 1 to survey the city and find all the specific files and classes related to database connections.
And older systems would literally stop right here.
Yeah, the detective would be standing in the right neighborhood, staring at 50 different houses, and we just have to start guessing which one is hiding the suspect.
But Arise arms the detective with Tier 2. This is the data flow slicing we discussed, utilizing a specific tool called getDataFlowSlice.
So Tier 2 is the detective dusting for specific footprints.
Yes.
Once they find a suspicious variable in that neighborhood, maybe a variable called timeout duration, they use Tier 2 to trace those footprints.
And the tool follows the variable backward, leading the detective straight to the exact line of code where a configuration file was loaded incorrectly.
It's brilliant. But the detective still has to present this evidence, which brings us to Tier 3.
Right, Tier 3 revolves around context bundling, specifically a tool called Build Context Bundle.
Because our detective has a strictly limited notebook. In this case, the AI's repair subagent has a hard limit of 8,000 tokens.
Exactly. 8,000 tokens. They cannot bring the entire city block or even a whole house into the interrogation room.
If they dump 1,000 pages of raw code on the desk, the reasoning engine will just hallucinate or lose track of the core logic.
So Tier 3 allows the detective to tear out all the useless pages. It neatly packs only the exact lines of code, the specific data flow footprints, and just enough surrounding structural context into a perfect, airtight 8,000 token bundle.
Wow.
And what is so striking about this specific 3-tier approach is how perfectly it mirrors human developer psychology.
How so?
Well, when a senior software engineer sits down to debug a massive system they've never seen before, they do not just open file after file and read the code top to bottom.
Oh, definitely not.
They perform iterative, multi-granular exploration.
Right. They jump around, they look at the high-level architecture to find the right module, then they zoom in to inspect a specific function, then they trace a single variable's value as it passes through a few lines of code to see where it breaks.
Exactly. Arise successfully aligns automated AI systems with actual human debugging workflows. It stops treating the codebase as a massive static document to be read.
And starts treating it as an interactive environment to be queried.
Exactly.
So the AI can trace footprints perfectly in a controlled academic environment. But human-written code on GitHub is, notoriously messy. It's undocumented, full of weird workarounds. Spaghetti code, basically.
Oh, the worst spaghetti code.
Does this rigid mapping system actually survive contact with the real world?
Well, the researchers put that to the test using a benchmark called SWE Benchlight.
Okay, SWE Benchlight.
And I want to be clear, this is not a synthesized toy data set designed to make AI look good.
Right.
It consists of 300 real, notoriously difficult GitHub issues pulled from 11 major, widely used Python repositories. We are talking about massive projects like Django, Flask, and scikit-learn.
Wow, okay, so these are real bugs that drove real open source developers crazy.
Absolutely.
What model did they use to power the reasoning?
For the main engine, they utilized the Qwen 2.5 Coder 32B Instruct backbone.
Oh, the 32 billion parameter open source model?
Yes. And the researchers specifically chose a model of this scale because smaller language models tend to suffer from tool use amnesia.
Tool use amnesia, that's it.
It's exactly what it sounds like. When a smaller model has to chain together 5 or 10 different tool queries in a row, it often forgets its original goal or just completely loses the thread of the investigation.
All right, it gets distracted.
But the 32B parameter model had the reasoning stamina to actually execute the full loop.
Okay, so you have a highly capable reasoning engine paired with this new X-ray toolset. How did it perform against those real-world bugs?
The jump in performance is staggering. They compared it against an unmodified SWE agent baseline, which is already a very robust system.
Okay.
Arise improved function recall at 1 by 17.0 points.
Wait, a 17-point jump in its ability to look at its very first guess and have it be the exact right function.
Yes, and line recall finding the exact broken line of code on the first try that jumped 15.0 points.
That's huge.
It is. And because localization is the ultimate bottleneck, these massive gains in finding the bug translated directly into fixing the bug. End-to-end, Arise achieved a 22.0% pass at one rate.
Let's break down pass at one for a second for everyone. That means 22% of the time the very first patch the AI generated completely fixed the bug and passed all the underlying unit tests without needing a second try.
Exactly. That is a 4.7 percentage point absolute bump over the SW agent baseline. And in the highly competitive world of automated program repair, a nearly 5% absolute increase on real, unvarnished GitHub issues is a monumental leap forward.
It really moves the technology closer from being a neat parlor trick to being an actual tool that could save a senior engineer, like 3 hours of frustrating debugging on a Friday afternoon.
Exactly. It's real with its impact.
Now, out of all the dense technical results in this paper, there was one quirky experiment that absolutely fascinated me. It's the explain slice ablation.
Ah, yes. The natural language surprise. It challenges a core assumption we have about how these models process information.
So the researchers looked at the output of the data flow tool, and the tool returns a highly structured JSON-formatted slice.
Right. It is basically raw data. Brackets, variable roles, node edges, and line numbers.
Yeah, and the team thought maybe the AI needs this translated into plain English to really grasp the context.
Makes sense.
So they created an explain slice tool. They essentially ran a secondary, smaller AI model to read the raw JSON and write a nice, human-readable 3 to 4 sentence summary of what the data flow meant right before handing it to the main reasoning AI.
Which seems like an entirely logical assumption to make. We call them large language models. We assume they want to reason in natural language.
But the result of doing this, it cost them 5,000 extra tokens of processing overhead per instance, and it did absolutely nothing.
Zero improvement in performance.
The metrics were completely identical whether the AI got the English summary or just the raw brackets and numbers.
And this tells us something really profound about how large language models actually operate at scale. At the 32 billion parameter level, these models are incredibly adept at consuming structured output directly.
Right.
When they look at raw JSON, file paths, and node edges, they don't see confusing computer code. They mathematically map the logic natively. They do not need a human-readable translation layer to understand the relationship between two variables.
It's like trying to explain a complex financial spreadsheet to an expert accountant by writing a 3-stanza poem about the numbers. It introduces ambiguity. Just give them the spreadsheet.
That's exactly it. The takeaway for anyone building AI applications or agentic workflows is vital here. Investing your engineering effort into providing better structured data, clean graphs, accurate edges, precise metadata is vastly superior to just slapping another LLM in the middle of the pipeline to summarize things into English.
Yeah, these models are smart enough to read the raw data, give them better, denser data.
Exact.
So we've seen this incredible success. By fundamentally changing how we present the environment to the AI, moving from a flat architectural blueprint to an interactive data-flowing X-ray, we've unlocked a whole new level of autonomous reasoning.
We really have.
But Arise isn't flawless. It has boundaries.
Yeah.
And understanding those boundaries tells us exactly where the future of software engineering is heading next.
Right. The most significant current limitation of Arise is that its data flow slicing is strictly interprocedural.
Meaning the X-ray vision stops at the boundaries of a single function.
Exactly. When the AI agent says, trace this variable backward, the tool can seamlessly follow it to the very top of that specific function. But if the variable's value was corrupted in a completely different function that was called from somewhere else,
The trail goes completely cold.
the analysis cannot bridge the gap between two separate procedures. In fact, during the evaluation, 45% of Arise's failures were categorized as wrong file errors, specifically because the data flow couldn't jump across those module boundaries.
Ah, so the plumber can trace the leaky pipe perfectly to the edge of the apartment unit, but the moment the pipe goes out into the main hallway, they're blind again.
That's exactly what's happening.
Well, why not just let the tool trace everything everywhere? Why not make it interprocedural?
Because computing interprocedural data flow across an entire enterprise codebase is computationally massive. Oh yeah. When you try to map every possible path a variable could take across thousands of interacting functions, you hit a combinatorial explosion. It creates a graph so dense and complex that it physically bogs down the system.
Got it.
Generating that map is simply too heavy for current practical implementation without slowing the agent's response time to an absolute crawl.
But, hardware always scales. Compute inevitably gets cheaper and faster.
And that is the thought I want to leave you with today. Right now, systems like Arise are constrained by the practical limits of our current processing power, stopping at the function door.
Right.
But what happens in 3, maybe 5 years when hardware scales enough to allow full, unconstrained interprocedural slicing in real time?
Oh, wow. The entire building gets X-rayed at once.
Imagine an AI agent that doesn't just stop at the apartment door. Imagine an agent that can trace a single bug from a visual symptom on your mobile app screen down through the cloud backend API, across a distributed database architecture, all the way down to a core operating system library.
In a single thought process.
Yes. In a single, continuous, unbroken thought process. When an agent can instantly highlight the exact broken line of code across a million files, will human debugging become a relic of the past?
That's a wild thought.
We might soon look back at the way developers manually hunt for bugs today, with the same disbelief as a master plumber watching someone tear open every wall in a 90-story skyscraper just to find one single leaky pipe.
A fascinating glimpse into a future that is arriving faster than we think. Thank you so much for breaking this all down with us.
Thanks for having me.
And to everyone listening, keep learning, keep diving deep into these sources, and we'll catch you on the next one.